In this video, we're going to have a look at how you calculate percentage yield. So percentage yield tells us about how successful our preparation has been, how much of our reactants did we manage to convert into our products. So we would normally, when we're doing a reacting mass calculation, we would assume that if the ratio was 1:1, 1 mole of reactant would make 1 mole of product. If the ratio was 1:2, 1 mole of reactant would make 2 moles of products. But how successful are our conversions? They're not always going to be 100% successful. So what we would do is we would look at the actual yield of the product over the theoretical yield. And that actual yield is usually the number of moles. So we're going to use moles again in our calculation. So the theoretical yield is the number of moles you expect. So we're going to put that down here. That if you were getting 100% conversion, and your actual yield is the number of moles you actually form. We're going to put that up here. So it's like having a test mark. In theory, you could get all of the test right. You could get 40 out of 40, but you actually get 38 out of 40. What percentage is that? So that's what we're doing. How much did we actually get compared to how much we theoretically could have got? So here's an example question. It says ethanol. So we're going to start with ethanol, which is this thing here, CH3CH2OH, can be oxidized to form ethanoic acid, which is over here. We can look at this equation and see that the ratio is 1:1. 1 mole makes 1 mole. And it says in an experiment, 2.3 grams of ethanol were used to produce 2.01 grams of ethanoic acid. So the first thing we would need to do is work out how much ethanol we started with in moles. Remember, chemistry is about moles, so we want to do mass divided by MR. So we add up the MR of ethanol and get 46. And so we've got 0.05 moles to start off with. Now, since the ratio of ethanol in the balanced equation to ethanoic acid, the product that we're trying to get, so we've got ethanoic acid here and we've got ethanol here. Since the ratio is 1:1, then the theoretical, so the ratio we get from just looking at the numbers in front of stuff, the theoretical amount of ethanoic acid we could form would be the same as the moles of ethanol we started with. In theory, we should be able to make 0.05 moles. How many actual moles of ethanoic acid did we make? And that is where we're going to use the mass of ethanoic acid divided by the MR. So we're going to add up 12 and 3 and 12 and 16 and 16 and 1. We're going to type that on our calculator. So this is how much we actually got. So our percentage yield, we actually scored 0.0335 in our conversion. The maximum we could have got was 0.05. And if we express that as a percentage, we're going to see that 67%. Why might it not be 100% though? So why did we not get it all right? Why did we not convert it all? Well, there's lots of things that could happen. Your reaction didn't actually finish. You didn't get to the end. You didn't get a complete reaction. Maybe some other reactions also happened. You got some other byproducts or side products. Maybe you lost some products when you moved it from the conical flask to the beaker to the evaporating basin. Maybe there were some impurities in the starting materials, and so they didn't actually, when you thought you had 2.3 grams at the beginning, you didn't really have that. Let's have a look at another example then. Calcium carbonate, CaCO3, so calcium ion 2 plus carbonate, CO3 2 minus, decomposes, so breaks down on heating to give calcium oxide, which would be CaO, and carbon dioxide. What we've got in our numbers is we've got 12.4 grams of calcium carbonate are heated, and then it tells us 90% converts into products. So it's telling us that the percentage yield is 90%. And it asks us to calculate how much calcium oxide we would make. So remembering we're only making 90% of what we should make in theory. Let's just start with moles of calcium carbonate. So again, mass over MR. So if you add up calcium carbonate, and work out the moles. Now, in theory, the theoretical moles of calcium oxide, so the amount that we should be able to make, is 1 to 1, so 0.124. But we actually make only 90% of that. Our conversion is 90%. So we work out what 90% of 0.124 is, and it comes out to be 0.111. This is still moles, we're just converting moles. So then we finish the question off with mass is Mr. Moles. And we add up the MR of calcium oxide, keeping it all on our calculator, and we get 6.25 grams. So we've got a third example. A student prepares a sample of magnesium hydroxide by reacting 25 centimetres cubed of 0.4 mole per decimetre cubed magnesium nitrate with 30 centimetres cubed of 0.75 mole per decimetre cubed potassium hydroxide. It says show by calculation that potassium hydroxide is in excess. So this is proving who's the limiting and who's the excess reagent. So to do that, we find the moles of each one. These are volumes and concentrations, so moles are very clever. Noticing that 25 centimetres cubed is not the same unit as moles per decimetre cubed. So we convert. So we work out how much magnesium nitrate we've got, which is 0.0100 moles. And how many moles of KOH, potassium hydroxide, have we got? So 30 centimetres cubed times 0.750 moles per decimetre cubed. So that's 0.0225 moles. Now, in theory, 1 mole of MgNO3 needs, according to the ratio, it's a 1 to 2 ratio, needs 2 moles of KOH. So 0.0100 moles, that's what we've got here, of Mg brackets NO3 would need 2 times that, so 0.0200 moles KOH. 0.0225, that's what we've got, is greater than 0.0200 moles. So KOH is more than we need. We would say it's in excess. So as the student obtained 467 milligrams of magnesium hydroxide, this is over here, calculate the percentage yield. We've got an added issue now, is that we know the moles of 2 of these things, and we need to know the theoretical moles of the magnesium hydroxide. So do we use the magnesium nitrate to help us decide how much we could make in theory, or do we use the potassium hydroxide? Well, you need to use the limiting one, the one that had all used up, so not the excess. So use the limiting reagent to work out the theoretical moles. Okay, so let's have a look at the limiting reagent. Was the one that wasn't in excess, the magnesium nitrate. So the ratio between magnesium nitrate and magnesium hydroxide was 1 to 1. So the amount we could in theory make of magnesium hydroxide is the same as the moles of magnesium nitrate used, 0.0100 moles. How much did we actually make? So the actual moles is, we're going to do mass is Mr. Moles, or moles is mass over MR. 467 milligrams, let's convert that into grams, divided by the MR of magnesium hydroxide. So we want to do 24.3 plus 2 lots of 16 and 2 lots of 1. So that's 58.3. That's coming out to be 0.00801 moles. So what's our percentage yield? Actual over theoretical. And then we're going to express that as a percentage, and that is coming out as 80.1%. And I think our final example of a percentage yield calculation is here, using density this time. 1 centimetre cubed of methanol with a density of 0.79 grams per centimetre cubed. So that's here. Reacts with an excess, so that means we're going to use the methanol in our calculation, and we're going to make 1,650 milligrams of methyl methanoate. So let's just work out how many moles of methanol we used. Well, to do that, we're going to need the mass of methanol. And at the moment, we've got the volume. Well, the volume is 1.5 centimetres cubed, and we've got 0.79 grams per centimetre cubed. So we've got 1.185 grams in total. And then moles is mass divided by MR. So that's how many moles we started with. Now the ratio is 1 to 1, so our theoretical moles of methyl methanoate is also 0.0370 moles. Our actual moles is mass. Again, we've got this in milligrams over MR. So we need to add up the MR. And then we're going to calculate the percentage yield by doing actual over theoretical times 100%. And we're getting 74.3%. It says now, in order to ensure a complete reaction, the student uses a 15% excess of methanoic acid, which is here. The density of methanoic acid is 1.22 grams per centimetre cubed. Calculate how much was needed to give us that 15%. So we go back up. The ratio between methanoic acid and methanol is 1 to 1. So the number of moles of HCOOH needed in the 1 to 1 ratio would be the same as the moles of methanol, 0.0370 moles. But if we want a 15% extra, the excess 15%, we need 115% in total. So the number of moles of HCOOH to give 15% excess is not to work out 15%, we need to work out 115%. And that is coming out to be 0.04255 moles. And then we can convert that into a mass. Mass is Mr. Moles, MR times moles. So we add up this methanoic acid and we get 46. And then we're typing that on our calculator and getting a mass in grams. But the question is what volume given the density. So volume is mass over density. And if you type that on your calculator, you're going to get 1.60 centimetres cubed.